So I thought I'd record this video to talk to you more about using applets rather than Dr. Stevens, rather than the table. Um, so this is about, it's in the section in the textbook that talks about the central limit theorem. Now, what if I didn't realize that this was from that section? The flags that tell me this is that now instead of one potato, I'm dealing with four potatoes. So now I'm into the sampling distributions. Now, um, there's some other issues. We only have a sample size of four, but we won't go into those here this week. Okay, but what does matter is it changes the standard deviation when a sampling distribute. If you watched that Mr. Nysick, whatever his name is, there, the guy, the orange hat guy, he talks about piles of p hats. Well, and then you just change the sample size, the variation gets smaller. And in this case, it's only a sample size of four, so it cuts the standard deviation in half. So how do I do the calculation instead of, if I were doing z-scores now, I would say, let's see, less than 10. I would say 10 minus 8 divided by the zero point 0.6, and that is z-score. Then go look that z-score up in the table. The great thing about having access to applets is, here, let me move this, let's see, just a minute here. Can I send this back? I know I can, I just don't know how to do it this second. So let me just move these out of the way. So I use the David Lane calculator, and the mean, means the same. I got to change the standard deviation to that new standard deviation, and they said below 10. And they're showing me almost 100%, almost all of it. Now, why is that? Why is that such a high probability? Well, 10. If you look at the scale on the bottom, a bag of 10 potatoes, probably somewhere around here. Do you see how almost all the distribution is less than that? It's more than three standard deviations above the mean. So that's going to mean it's way out there. So um, it's pretty unlikely that I'm going to get a bag of. I mean, how do I want to word this? To answer this question, it's almost 100% sure that I'm going to get a sample of four potatoes that'll have an average less than 10 ounces. And the reason that is 10 is so far outside of the realm of this distribution, it's unlikely that that'll happen, really, is where we're going with this. So yeah, I'm going to go, can I say 10 is going to be an upper limit? Well, most definitely, because, it's way out there. Probably can go less than that. But this saves us from doing the z-score and then using the table to find trying to find the probability. Okay, so then here, give me a minute. Okay, for part B, now we've got a sample size of 20. So took the 1.2, the population standard deviation of 1.2. I divided by the square root of 20, and I got 0.268 or so. And then it's still the same thing. What's probably going to less than 10? Well, if it was when the standard deviation was bigger, it was almost 1. This is going to be 1. So take a look at this distribution. See how much smaller three standard deviations away from the mean is? So, and you notice how they're saying it's a 100% chance of that happening? That's because the 10 is, let's see, this isn't even a distance of 1. So a average weighted 10 will be way up here, way above expectations. So yeah, it's a 100% chance we're going to get an average of 20 potatoes that'll weigh less than 10 ounces. That's asking. Or we could the other way, it's very unlikely we're going to get an average of 10, if the mean is 8, and with a sample size of 20. That's more what we're going to do in a couple of weeks. Now the next question: suppose that Carl's bags randomly, he samples six potatoes. What percentage of the bags will have a mean weight between 7.2 and 7.5? Well, if you've done enough of these, in order to do this by hand, we'll have to do, what we do well by hand, maybe I'll get it set up. We'd have to find the z-score for 7.5, so 7.5 minus 8 divided by the standard deviation for sample size of 6, which is 4.49. Get that number, get that z-score, look up the probability for it. Then we'd have to do the same thing for the upper end of 8.5. 8.5 minus 8 divided by 0.49. get that z-score, find that probability, then subtract them. The beautiful thing about this calculator, and most of these calculators, all you've got to do is input the mean, the new standard deviation, and then we'll say between, and that's the probability. And that's what you'd get if you did it, by hand. Okay, so I encourage you to use this. And if I haven't said this enough, I encourage you to use this David Lane calculator. Though your graphing calculators do it, there's other ones out there too. What I like about this calculator is that you can see the graph of what's going on. Okay, very last question now. Let's come back here. So for this last one, they're saying, hey, we got a bag of 6 potatoes, and my bag weighs 42 ounces. Am I cheated? Well, let's see. I know that the mean of this distribution is well, let's see. Let's do this. I know that 42 here. I know that 42 ounces divided by 6 potatoes is an average of 7 ounces per potato. If the mean's 8 ounces, are we really low, or are we just the luck of the draw? So let me go back and pull up that graph that I just deleted. So we see that so 7 ounces. So this is with the standard deviation for the six sample size of six, right? And we see that the mean's in the middle, and we see that at 7 ounces falls down here. That's more than 2 standard deviations away from the mean. I mean, if we were to look up the probability, it would be less than 5%. So yeah, they got a case. I think that bag of potatoes is unusually small because it's kind of an outlier based on this distribution. So that's how you would answer that. And you could certainly go find the probability in either with this or with the table. But because it's more, if we're almost thinking of the 2 standard deviation outlier test here, um, and that's how come I made that decision. So hey, here's one problem using applets with a standard deviation, a central limit theorem. So now we're into this normal approximation of the binomial distribution. This is very similar to how chapter 5 ended. We were finding the mean standard deviation and then using that to work with the z-scores. So what we can do now is we can pull it into the normal curve and use calculators or whatever they want us to use. You find the probabilities. But again, just like what we need to do here is we need to do a condition check. Make sure that this is going to make a normal distribution. And that is, you're going to take the probability, so in this case 48% of Americans, and we have 220 employees. If we multiply that, is that answer bigger than 5? And sure is, it's almost half. And then so to do 1 minus the the probability or that percentage. So that's 0.52, and that times 220 is also bigger than 5. So because this is true, we can use a normal approximation, a normal distribution to approximate this binomial distribution. So what we got to do is we got to find the mean and the standard deviation. So here, let me erase this since we've got this done. So the mean we did in chapter 5, and we found that we're going to do 0.48 times 220, and we get that number, and then the standard deviation is the square root of that number times 1 minus the probability, so that's 0.52. And then we'll take the square root of that answer. So then it's asking us, is it unusual to find only 85 happy employees if in this distribution? So, well, we can certainly do just like what we did in chapter 5. We can say find a z-score, 85 minus 105.6 divided by 7.41. We can calculate that number and see if it's more than 2. It almost looks like it's going to be. Or -2. We got beyond -2. So 85 minus 105.6 divided by 7.41. I'm getting a z-score of -2.78. Well, that's way more than 2 standard deviations away from the mean. So It would be very unusual to get a sample of 220 employees and find that only 85 of them are happy with their job. And then the last part, well, how unusual? Here they want a probability. I mean, so what we can do is we just go to a normal curve table and use that. Here, give me a second. I'll have a copy of that. So we're going to use this table to look up negative 2.78. So negative 2.78. So I'm seeing 0.27%. I mean, that's the probability, as in a percentage, that'd be 0.27. So a pretty small. So I got to copy this table, and we're going to look up negative 2.78. So that's the probability as a percentage. That would be 0.27, which is pretty small. So how unusual? Well, let's see. A couple of ways to do that. We could say 0.27%. Only 0.27% of the time could we expect that. We could say if it's 0.00, make it sound really small. We could say that's 27 out of 10,000 because it's tenths, hundreds, thousands, 10,000ths. So 27 out of 10,000. That would make it sound pretty small. I'm pretty I mean, if so, some interpretations for this. Um, with that lower probability, either the 48%, the results from that old poll that says 48% of Americans are satisfied with their job, either that's off or else this company has a problem. Or at least the 200 says a company with 220 employees. So I would suggest that maybe this company is having some issues that they probably should resolve. Okay, and again, you could use David Lane for this. You wouldn't need to do the z-score. I mean, it wouldn't tell you the z-score, but you get the probability. Okay, I guess that's enough for this problem. So another one, and of course, to start exercise, you can go look the answer up in the back of the book how Dr. Stevens did these. But I know that, well, let's see, is 16, let's see, that's about 1/6. 1/6 of 250 is certainly more than 5. And 5/6 or 0.833 of 250 is also bigger than 5. So this is the normal. We can use the normal approximation. For you can use a normal curve to approximate this binomial distribution. So let's find the mean. So the mean would be 0.166 times 250, and the standard deviation would be 0.833. Sorry, I screwed that one up. How do I undo my thing? It'll be the square root of 0.166 times 250 times 0.833. And then we'll take the square root. Let's see, if you don't mind me just running the video while I do this. Times 250. I'm getting 41.5 and then 0.833, and I'll take the square root, and I'm getting 5.88, doing some rounding. So there's the mean, there's the standard deviation. I'm going to go use David Lane for this. Is it an unusual event? I mean, you could certainly do the same thing, find the z-score, go look it up in the table. I didn't run David Lane in the last one. I'll do it here. So they're asking us how unusual it would be to get a sample of 250 adults where 50 or more were uninsured. Well, if we look at the distribution here that this applet gave us, we see that here's the 50. That's less than 2 standard deviations away, so it wouldn't be considered unusual, and that means it's 7% chance of that happening. So I mean, it's more than 5, so it wouldn't be an unusual result. Now, is it high? Yeah. Is it statistically high? Maybe not really, based on that that 2 standard deviation rule. The thing that I was hoping you got out of watching all the videos about sampling distributions is every sample is not going to give, like if we go out and sample 250 other people, find the number of them that are uninsured, and we repeated and repeated and repeated, it's good. They're going to fall in a normal, right? Remember the pile of p hats? So it would be the pile of p hats would be piled around. It's just the trick is, do you get a p hat outside that acceptable range? And this we try to say, the middle 95% or two standard deviations. So we couldn't make the argument that it's unusually high. Okay, so this is kind of a glimmer of where we're going with this after the exam. So I hope this helps. Give a yell if you need help, and we can do some more in the forum.